All right, I'm going to get started. If more people come, then they're not going to miss much in the first part. Okay, so I'm Moses Nakamura. I work at Twitter. First things first, this talk is scaling reliability, so you want to add a 9. And in this context, the 9s that we're talking about are 9s of reliability, or we're talking about, like, say you want your success rate to be 99.9%. We would say that's 3 9s. An example, maybe if we went in to add another 9, that would be going to 99.99% success rate. I'm Moses Nakamura. I work at Twitter. I work on an open source project called Finagle. I'm on Twitter. My handle is @mnnakamura. I would appreciate if you followed me because I'm paid directly proportionally to how many followers I have. So the core idea of this talk is that as your organization scales up, the reliability challenges that you're able to deal with and want to deal with and sort of need to deal with for your business are going to change also. And I'm going to talk about the different phases that your organization, or the different classes of problems that your organization is equipped to deal with and wants to deal with, change over time and as your organization scales up, and different ways that Twitter solve problems with this, specifically in the RPC space. And many of these problems we solved with Finagle. So if you want to take advantage of our solutions for them, feel free to go check out the project. So one question is, who cares about reliability? Twitter cares a lot about reliability. I think probably if you have any kind of business that's providing some service to your customers, you're going to care a lot about reliability. Twitter cared a lot about reliability because in some ways, when you mentioned Twitter a few years ago, actually more like 7 years ago at this point, people would think of the fail whale, which is this nice little image, which basically was a sign that Twitter was down again. And that's not really what you want your business to be known for. You probably want it to be known for whatever your business is actually supposed to be doing and not being able to do whatever your business is supposed to be doing. So one question is, how do we measure reliability? There are many different ways we can measure it. One of them is uptime. This might be uptime per quarter or uptime per week. Where you just say, how many minutes were people able to get whatever content they want from me, versus how many minutes were there over that period. Uptime is probably the most common unit of measurement, and usually when people are talking about 9s, they're talking about 9s of uptime. There's also dollars. So for example, if you're not able to, if you're like Twilio and you go down for an hour and people are trying to pay you for your stuff, but you can't, or you need to refund people for something that they already paid for, those are dollars that you've lost. Another thing is going to be success rate, the mean time between failures, and the mean time to resolution. So I introduced Finagle briefly before. Finagle is an extensible RPC system, and we use it for every service at Twitter, which means that pretty much every service has a bunch of reliability guarantees built into it from day one. And Finagle has grown somewhat organically and somewhat from the top down. We saw that as we were scaling our organization, we weren't able to scale the reliability concerns as linearly as we wanted to, and Finagle became a tool to help us do that. Okay, so the first step that your organization is probably going to take as far as managing failures is going to say teams must own their own failures. And this seems like a pretty basic thing, but in many organizations this isn't really the case. Like sometimes devs will push something out and then someone else like ops or DevOps has to go and own the failures. Usually what this ends up meaning is that there end up being a lot of background noise failures and just weird hardware things that might happen in your data center that just go ignored because it isn't such a bad experience for the customer. But as you force teams to own their own stuff, then they'll begin to be able to look at this stuff more deeply. So some examples of background noise failures are gray failures, like for example, transient failure, Heisenbugs, which are things which are non-deterministic, temporarily overloaded hosts, for example, when you have weird load balancing, like if you're using a random load balancer, and crashes. Bad remote hosts are usually because of hardware failures or a remote peer is getting into a state and hasn't been shut down properly yet. So let's say we have a probabilistic failure. When the caller talks to the receiver, it's going to succeed with 90% probability. What are some things we could do to deal with this? Sorry, could you repeat that?
Prepare for failures.
What would that entail? What's an example of that?
Work around errors, be prepared not to if responses fail.
Yeah, so if there's a failure, just sort of have like a good backup plan, basically. Another thing is if this is really probabilistic, we could just try it again. If it fails the first time, but we don't know whether or not it's going to fail the second time, then we could just do it twice and then you're going to have a higher success rate. So in this case, we added 2 more retries and suddenly moved our success rate from 1.9 to 3.9. It's like a pretty simple approach that can have pretty good impact. Retries are of course not always an option. For example, if you have a non-idempotent write and you don't know whether your write happened or not, you don't want to, for example, bill your customer 3 times just because you weren't sure whether or not the write happened. Another thing that can happen is sometimes when you have one remote peer which is having a bad day, for example, one remote peer that's in a bad state, then probably you want to be able to route around that peer instead of continuing to have them fail your stuff. So one thing you can do is just count how many times a remote peer gives you a bad response, and depending upon how many times that happens, change how often you talk to each of them. So in this case, there's one remote peer, which keeps on giving you bad responses. And so your clients notice this and say, OK, I'm going to stop talking to them. There are many different strategies for failure detection. It's like a very widely studied field, I would say. We've had pretty good success just keeping track of success rates with an exponentially weighted moving average. And you can do that either for like a number of requests or some duration. And there are lots of different ways of tuning this depending upon what your use cases are. OK, so let's say that there's an individual host that gets overloaded. What options do you have? So someone said use the other 2. That's a really good idea. That's sort of going back to what we were talking about before, where you figure out, OK, instead of talking to the one that's bad, we're going to just route around this one. Sometimes it's difficult for the client to tell how unhealthy a remote peer is, though. So if the server has better information that it's getting slow, then other than the client just load balancing and saying, oh, hey, I don't want to talk to the slow one, then the server also has the option of saying, hey, don't talk to me. So typically this is called a NAC, and there are lots of protocols which have these built in. For example, HTTP2 has RSTs built in, which can be used as NACs. RSTs have lots of different possible error codes, and there's one which is like enhance your calm, which you can use as, hey, I'm overloaded, and your clients can have better information rather than just, oh, hey, that remote peer type is weirdly slow, that they shouldn't talk to that one as best. So beyond these sort of basic background failures that happen all the time, once you have a team that's dedicated to resiliency, then suddenly there's other kinds of things that we can tackle. This begins to become more of an issue as we scale up our stuff. So one example is the microservice architecture right now is pretty popular. This is very neat, but as we add individual components, if each app has a 10% chance of failure, if suddenly each tier has a 10% chance of failure, then our overall success rate is going to go down to like 60%, which sort of isn't too good. But then if we're able to do something like add retries, then suddenly we can go up to a much more acceptable success rate, like 99.6, which is not great, but there's more work we can do. Basically, this just means that we have smaller and smaller room for error that will appear as really user visible. Another class of errors that we might want to focus on, other than just the background noise failures, are failures on edges, or where we introduce some change into the system, which might be a new deploy, or it might be turning on a feature toggle, or your client deploying, or the receiver who you're calling deploying. All of these things can introduce lots of changes into your system. And it's useful to be able to have tools to deal with these kinds of changes. One example is when your remote peers are deploying, if you don't know how to handle it gracefully, if they can't do graceful shutdowns, for example, then you might see lots of errors. Also, when you get new code, sometimes there's bugs in it. I've stopped writing bugs, but for some reason, many other people at my company still write bugs. I've tried talking to them about it, but they're not that responsive. Okay, so one question that we might want to know is, we have a caller. In this case, we have 3 instances of some service, and they're all talking to 3 instances of some other service. What kinds of things might we want to know about what's going on here? So here's some things. We have this service A, which is talking to a service B, which then talks to a service C. And what's happening here is A makes request to B makes request to C isn't able to hand back a successful request to B, so B does a retry to C, which is then successful, and then B responds back to A. So what kind of information might be useful to know in this scenario? Did someone say something? Okay.
Number of internal retries.
So one example is number of internal retries. That's a good idea. Anything else? Like if you were instrumenting this, what kinds of things might you want to know about what happened in this if this was your service? Okay, why did it fail? That's another good example. Maybe we'd add logging for exceptions or something like that. Anything else? Sorry?
The request payload.
Yeah, what was the request payload? So if this isn't a particularly high throughput service, then we might be able to just log every single request. Or if there was an interesting request, we might want to just log the request payload for those specifically, or sample them or something like that. Okay. Those are all good examples. Some other things we might want to know is the latency of a given request. So maybe the latency of the overall request, then also the latency of individual requests. As you mentioned before, it would be useful to keep track of how many retries we did, how many failures we have, how many successes we have. And if you have a distributed tracing system, it would also be nice to just keep traces of all this stuff in logs. So observability gives us much more power when trying to understand our services. Instead of just trying to reason about it from the code and like, this is what should be happening, we can actually inspect what actually does happen. So observability is pretty important to have in order to keep your services live. We want to have metrics like time series stuff, which you might get in something like Datadog or Graphite, logging, and in theory, you can persist your logs. It should be a pretty cheap way of keeping track of lots of events. Tracing, distributed tracing is enormously useful if you're able to set it up, although it requires often a pretty consistent environment. It's really useful to have your configuration information. For example, if you know that there's a bug with services which are configured in a specific way, then instead of having to go and like redeploy every single service, you can just go and find which ones are configured in that specific way and fix them. And also, it's useful to know who your remote peers are. Okay, so for people who still write bugs, sometimes they find that there's a bug in their release. What are things that we can do to mitigate the impact of these bugs and releases? Rollback. That's a good example. So is what you're imagining, you go and you deploy to every single node and you see, oh, my website is totally down, and then you do a rollback? Okay, is there any way where we can avoid getting all the way to the point where your entire website is down? So an example I was given here was do a canary deploy to only one, watch what happens. That's a really good idea. So we can do a canary, and if that canary falls over, then you know probably you shouldn't roll out to the rest of your services. You can save doing the full rollback. You just have to roll back the one canary. So I mentioned before that sometimes you can have failures while you're rolling. So imagine that we're doing a rolling restart here. So we're taking down this one receiver, and while it's down, the callers don't know the receiver has gone down yet. So they keep on sending requests to it, even though they're going to fail. So instead of continuing to send requests, if the receiver is able to do a graceful shutdown and drain its requests and let its clients know that it won't be able to handle requests anymore, then we're able to have a much neater solution here. So in this example, first, there are lots of requests which are being sent. You start sending responses. Then we have basically, go away, I'm going to die. And then the client knows that no more of its requests will be satisfied. Actually, in this one, the response is weird because it's dead. And this one says actually go away. And again, if we use HTTP2 or Twitter has a protocol called Mux, which also has this built in. If you send the go away, you can say this is the last request which I'm able to satisfy. Okay, so after some point, we begin to get into the realm of the kinds of problems which possibly only dedicated teams are going to be able to help with. Another way in which when you scale your organization up, you begin to keep on having more problems is people are basically bug-producing machines. And as your team, say, doubles in size over 4 months or whatever team growth you're so proud of, your bug production will also double in size over those 4 months. So another way in which we need to be able to lock down resiliency errors more and more effectively. So some of the kinds of issues that we'll have won't be necessarily planned events, like these kinds of edge changes I was describing before. Sometimes there'll be unplanned events. One example would be just an overload, like for example, you get written up in the New York Times, or you appear on Good Morning America or something like that, and suddenly everyone is there, and you didn't realize how much attention you're going to be getting. Another example can be a retry storm, where because the remote peers are all failing, you send a bunch of requests to them, and they fail, then you retry them, and then that causes the overload to be worse, and so it fails even more requests, and ends up being this sort of awful positive feedback loop. There can also be a hot shard problem. One sort of weird thing that Twitter once ran into is, I'm not sure if you've seen this movie Castle in the Sky before. It's a popular anime film from I think the late 80s or early 90s. And in Japan, when they air it, there's a tradition that when a specific scene comes on, at that very second, everybody tweets this magical word of destruction, which destroys all computers. In particular, destroys Twitter's computers. So that's like a weird event that can be difficult to predict, unless you're watching the Japan broadcast planning, which we now do. There can also be poisonous library deploys, which aren't necessarily caught immediately. And there can also be problems when your mean time to recovery is slow, where if there is this sort of unexpected problem and you aren't able to recover quickly, then that can make, for example, your uptime much, much worse. Okay, so I mentioned before we can have these retry storms where there's some level of overload, so you send more retries, which then makes the overload worse. One way in which you can solve these is having a retry budget where we say no more than X% of these are allowed to be retries. So you can say, I was able to send like 80 successful requests. I'm going to say only 25% after successful requests are allowed to be retries. This limits the overall overload that your clients send to a remote peer. Another example is this cluster overload case, where, for example, some people want to rush and say a magical word which destroys computers on your website, and there's just a bunch of natural traffic that is too much for your service to handle. What are some options we can take in this case? So one example would be rate limiting. What might rate limiting entail?
So the caller is doing requests to the receiver because of something that's being caused to do, deny those requests coming in and shed load in some way.
Yeah, so some kind of load shedding. One sort of simple way of doing this is if you already have retries built in and you know that this is going to be a temporary overload, then you can have exponential backoff and jitter added to your retries. Another thing is, as you mentioned before, we can shed load. So here's the case where we're sending a bunch of requests, we're not getting as many responses back as we expect. If every single remote peer is saying, hey, I'm having a bad day, then your client can know, maybe I should back off for a little while and start dropping some proportion of requests. So in this case, we might say, because we're only seeing like an 80% success rate, why don't we try dropping 10% of our traffic and see if our remote peers recover. In a case where they're only able to handle up to like 95% of the traffic that we're sending them, this would allow them to recover up to 95%. If we guess 90%, that's still better than the 80% that we're seeing right now. Something that you might run into also is if you have, for example, if you have bad neighbors who are stealing a bunch of CPU time from you in AWS or something like that, or if you're running something which says that if you try to be a bad actor and take too much CPU time, then you're going to be throttled, then you can also tell people to back off based on that. So in our case, we often have services get throttled when they're spending too much time doing garbage collections, which sometimes indicates a GC spiral. So we use this as basically a sign that says, hey, I'm about to go into a GC death spiral. How about you stop sending me requests so I can stop doing that? So we have a little thread running in the back of our process, which just goes and checks and says, okay, am I being throttled? How badly am I being throttled? And given that, should I start asking my remote peers to back off? So another example of something that might happen is imagine that you deploy some new service which can send poisonous requests, which can poison the remote peer, but also remote peers down the line because of some new feature that's been turned on, or some insidious library feature which has appeared like a ticking time bomb in many of your services already. You don't know which ones, and you want to turn it off, but in order to figure out which ones have been deployed with which code, it'll be very labor intensive. These kinds of issues can be solved neatly if you have feature toggles for your library code as well as for your regular stuff. So you can sort of imagine we're sending all these requests, and because of some new feature we've turned on, the second one is poisonous. And so because of this, the remote peer is only able to send one response. After the poisonous one, it's not able to send any new stuff. By having a toggle that we can turn on or turn off, when we have a new feature, we can have a little more confidence when we're deploying them. So one example might be, instead of turning on for every single remote service, for every single service, you could turn on for like 1% of services at a time, or 5%, or 10%. Another example might be when you notice something is bad, you can just use it as a kill switch, so that at runtime you say, okay, this feature is not working out for us, it's killing a bunch of services, we're just going to turn it off and figure things out. Another example of a way that you can help avoid this problem is sort of going back to what we were saying before about canarying. If you have different staging environments where staging nodes only talk to other staging nodes, you can help make this a little bit easier to work with. So imagine that you have some new release of your software, and first it goes out to staging, where first the caller goes and poisons the receiver, and you can sort of see, oh, staging really had a hard time after we sent out this poisonous library and it ran for like a couple days. So another way that we have of helping with this is we have this naming system built into Finagle called Wiley, and one of its tools is these dtabs, which are things you can annotate a request with, which will say, for example, like, hey, this should only go through staging servers. That way, instead of having to manage your staging environment totally separately from the prod environment, you can simply annotate certain certain requests as being specifically for staging without having to say, And these environments will be totally sealed off from these other environments. You can just do it with your naming system. So one thing is, everything I mentioned today is things that are built into Finagle, but these are, of course, not the only ways in which Twitter helps itself stay resilient. Basically, we're constantly working with many other different teams in order to get this to work all together. And everyone is thinking about the reliability of the website overall and how we can all work together. We work a lot with the observability teams so that we're collecting the right observability metrics, but also we're not collecting so much that it's going to bankrupt Twitter. We also work with the automation teams that go and make tools so that, for example, when you notice that a service needs to be restarted, instead of having to go and wake somebody up to go restart that service, it can just restart it itself. We want to work with the deploys people to make sure deploys work the right way and don't go crazy. There's a great coordination team, which makes sure that when there's a big incident, things get coordinated properly and people aren't just all running around doing a lot of duplicate investigation. There's the site reliability engineering team, which is making sure that reliability best practices get spread through the organization. And we also make sure that we're all practicing for this stuff so that when there is some natural disaster, whether that's getting some kind of big boost in traffic or a literal natural disaster like a hurricane coming and striking your data center, that we know how we're going to behave in that case and that we're able to handle it. Another big thing here is failing collaboratively. So it's difficult for your company to make progress if everyone is sort of failing by themselves and not telling anyone else about their failures, because it means that you're never able to learn from other people's mistakes. You're only able to learn from your own mistakes. So one really good thing that we do is we have just a global list of all incidents. That's just one big Jira project. You can organize it however you want. But on the Finagle team, I can go and see incidents from every single other team and why they happened and try to infer whether there's anything Finagle could have done in order to make that incident less painful for our end users. Another thing that we mentioned before is coordinating things. So we want to make sure that the resiliency efforts that we're doing in order to squash a particular kind of incident isn't also being duplicated by some other team, like for example the deploys team, which is investing a lot of their time in order to solve the same problem. Instead, we could better provide resiliency by saying, okay, you deal with that thing which is really your specialty, and I'll deal with this other thing which is my specialty. Another thing is making sure that you're empowering individual teams in order to make the changes that are actually necessary in order to improve resiliency. If people know what the problems are but can't fix them, then there's no point in knowing how you could fix the problem. Another thing is making sure that you keep history, and institutional knowledge is sort of one of the most difficult problems of maintaining institutional knowledge is one of the most difficult problems of running a company, but it's really important and really valuable if you're able to do it. And sometimes that's just telling war stories at a monthly event where people remember, oh yeah, there was this really bad thing, and maybe we should make sure that can never happen again. Or maybe that was why we had that one extra check that we just removed last month. Maybe we shouldn't have removed that. Maybe we should add it back in. Another thing is making sure that your postmortems are blame-free so that people are able to be honest and don't feel like they have to sort of redirect blame or cover for themselves when they're trying to get down to the truth of why the incident happened and how you can prevent it from happening again in the future. All right, that's all I got. Any questions? What's up?
Can you talk a little bit about what your tool or your project is actually doing to help with all of this, or what it technically does?
Yeah, so the question is, what does the tool or project that I work on, which is Finagle, do to help with this? And so just from the beginning, Finagle is a system for having one service talk to another service. So it handles everything from connection management to load balancing to naming to service discovery and failure detection and all these things. So the API that gets exposed to an end user is I have this thing which I can put a request in, and from there it goes to some individual node on some service, and you can get a response out of it. And one example of where this sort of opaque abstraction helps us is I send a request which then gets load balanced to a node which I know is healthy and is probably going to be fast and is in a data center that isn't failed over, preferably in my data center. If it fails to make a request because of some dumb reason, like for example, we weren't able to establish TCP connection, we're just going to retry that automatically. There are some retries which you can't do automatically, but for everything where we know that we didn't actually write anything to the wire, we'll just do it automatically. So we also have lots of connection pooling stuff baked in, and at the protocol layer, we have the knacking stuff, like for example, if you're throttled, you'll just start knacking automatically, or if you can also configure, oh, I don't want to have more than this number of requests coming into my server, and if too many requests are coming in, you can just start knacking requests. So we also have draining built in, and all kinds of other things. So Finagle is sort of taking care of almost everything that you want to do between two stateless services.
What are the language bindings?
The question is, what are the language bindings for it? And so Finagle is written in Scala, so it's anything on the JVM. So one approach that people have taken when they wanted to use Finagle's feature set but didn't want to be on the JVM is there's a company called Linkerd, which basically turned Finagle into a sidecar where you can then talk to it from any language you wish. It just is a little process that runs alongside yours. Yeah, go ahead.
How much of the things that are built in Finagle are assuming that you have a vast data center and lots of services behind it? If I have a single service machine, then of course somehow redirecting to another service doesn't work, or to another data center doesn't work, or let's say I only have 3, then even the canary might be tricky because that somehow takes 1/3 of my whole capacity away. Yeah,
so the question is, how much of Finagle assumes that you're in like an enormous environment? So at least at Twitter, we have some services which are enormous, like on the, at least enormous for Twitter. So on the order of like thousands of hosts. But there are also some services which aren't at that scale. And Finagle is used for both of them. So we expect that it should behave well. Often people have fewer problems when they're at a smaller scale, which is part of what I was talking about before in my talk. So I would say that you won't see as big benefits from using Finagle, but definitely it can still be useful. And there are different ways in which you can configure it if, for example, you're only talking to one remote peer. Although some pieces like load balancing won't be that useful for you. Yeah, so the question was, is Finagle on the client or on the server? And it has a piece which can be on the client side, and then also has a piece which can be on the server side. And so using that, people have constructed the proxy which you described, which is Linkerd. So yeah, it's all three.
So is it just strictly based on HTTP2 or something of that nature, or is it on its own protocol inherently as well?
Yeah, so Finagle was designed to be usable with many different protocols. So originally it was intended to be pretty extensible and still is to this day. So Twitter has made it work with memcached, Redis, Thrift. Actually, Redis was a contribution from Tumblr. We added a protocol we wrote called MUX, which is for in-data center RPC. We also have HTTP 1.1, HTTP 1.0, and HTTP 2, which is still somewhat experimental. And other people have, and also Finagle MySQL. And other people have written bindings for Postgres and protobufs and other languages or other protocols. Go ahead.
So then based on that, does that mean it's both protocol and body shaping in the sense that you can inspect the incoming message as well as the protocol itself to certain deterministic behaviors? Or, like in other words, I've got these headers in the message, so on and so forth, or the body, has these like protobuf, right, binary-ish format.
Yeah, so the question is, are you able to inspect the message as well as the protocol? And Finagle exposes different APIs depending upon which protocol you're using. So, like for example, it would be somewhat elaborate in order to support having a client which could speak both to a memcached server and also to a Thrift server. So when you're talking to memcached, you go and get whatever information you need from memcached. So we're probably not going to give you like the raw bytes, but if you wanted to infer what the raw bytes were, you probably could. And if you do need something where you have raw bytes, then you can build that yourself with Finagle.
So it's Scala. Is it extensible, and can you use like any JVM language for extension or only Scala?
So the question is Finagle extensible, and does it have to be extended from Scala, or can you use any JVM language? So it's definitely easier to extend in Scala, but people have extended it in Java. Oh, and it is extensible. People have extended it in Java, and we're constantly trying to improve the Java bindings. Sometimes Scala, unfortunately, doesn't make it that easy to make really solid Java bindings, but it's something we're working a lot on. And if you go and try it and find that you're not able to, please file a ticket with us and we'll help you fix it. As far as other JVM languages like Groovy or JRuby or Jython or whatever other JVM languages you're thinking of, I haven't tried with any of them. So my suspicion is if you're able to do it with Java and other languages have good FFI for Java, then it should be totally doable, but I don't know for sure.
So you mentioned the clients, and I totally get the whole, behind the curtain bit, right? Service to service and client to client in that regard. But what about, taking this example, JavaScript client, do you guys have libraries for doing that as well, send extra headers and so forth that are specific, to?
Yeah, so the question is, suppose there's like a JavaScript server or even maybe like in the web browser or something like that, which wants to, or yeah, on your phone, that wants to send messages along. How would you have it participate in the sort of Finagle ecosystem or Twitter ecosystem, whatever you want to call it. That's not something we have a super amazing story for right now, to be honest. So one of the reasons why we're working on this proxy, so other than Linkerd, we're also working on something similar, which we want to help make other services built in other languages be able to communicate and participate in the Finagle ecosystem in a much simpler way. Right now, when a new service gets built at Twitter, we can say, oh, just do it on the JVM. That's easy. But if Twitter acquires some company and they're using Go and they're using gRPC and whatever other things, then we don't want to have to force them to rewrite all their stuff in Scala. I mean, we acquired them because we thought what they were doing was already good. So we just want to give them thin shims that they can then use to participate. So I think that this proxy or a sidecar idea has a lot of legs and it's worth investigating, at least for us. You might find that's the case also. As far as things on the client side, it's not going to be easy to add a sidecar to whatever web browser you have, or like web application you have, probably. So
Yeah, I was probably thinking more like along the lines of like headers and like is there a specification for already certain headers that mean certain things as you go all the way through the path, you know, to, I don't know what you call it, right, Finagle ecosystem. In other words, from my phone, you know, to whatever proxy to whatever, and things that supposedly would be boarded on perhaps, so that you have all that data to associate with it.
yeah, so the question is, if you have some client, how can you have them like add headers that will have it be propagated throughout the entire system? And basically, we just have like a list of headers which are special, and people who are writing clients will add them. So that might be like, hey, I want this to be traced, which is like debug equals true or something like that. And it's just something that people know. Yeah, but in the future, we could write client libraries that would just add those headers for you, but we don't have that right now. And clients have like pretty diverse ways of talking to the servers, because there's not just whatever you have in like your Android client or your iOS client, but maybe you have other kinds of clients, and maybe you also have somebody who's running an iOS from like 4 years ago. So that might be like a totally different client than someone else. So when we're getting into clients that you don't control, that's getting into like a pretty thorny territory. Okay, well, it seems like that's probably it. Thanks for being here. I'm just going to hang out after the talk if you want to chat.